Uh, Good afternoon, everybody. Welcome back from lunch. Just give you guys a minute to get collected. I'll be moderating this next session on just the modeling session. We'll be starting out with an overview of some of my work. Unfortunately, I've inappropriately titled this, but I'll get into that. Then we'll move on to some of the work by Noemi Vergopolen and Sally Diamond afterward. So I'll just start off with myself. My name is Carlos Quintero. I'm an ORISE postdoctoral research fellow working under a joint agreement between the Forest Service and the NRCS primarily on a project looking to model and monitor forest soil moisture. We're primarily interested in high elevation, densely vegetated forested landscapes. And I'll just be talking about some of the work that I do there. So just a little bit about the background of soil moisture prediction and how we get at soil moisture information. You've seen this referred to as your three-legged stool. So we can get soil moisture information via in situ methodologies, that is your sensors that are in contact with the soils that you wish to measure. And these methodologies typically give us high temporal resolution and high accuracy at depth, but they tend to be point scale. And this causes issues if you want to relate these measurements to the greater landscape. We also have remote sensing measurements, which are valuable. They give us excellent spatial distribution, but as a consequence, we get low resolution returns. One of the drawbacks to remote sensing measurements is that we have poor measurement availability and accuracy at depth. Typically, as you've learned, that L-band is giving you returns at your top 5 centimeters. And while there are modeled products that'll get deeper, that's still one of the drawbacks to that technology. Their accuracy tends to be limited in areas of dense overstory. So the forested landscapes that we're interested in are issues for these remote sensing platforms. And then their accuracy is also limited in areas of high relief. Slope and aspect cause issues as well. Of course, there's methodologies that they put in place to get more accurate measurements, but the environments that we're interested in are an issue for remote sensing. And then there's also the process-based modeling approach, land surface modeling, and other modeling approaches can be put in here. But I'm primarily focused on process-based modeling. And the benefits to this approach to getting at soil moisture information is that you can get a high temporal resolution product, a high spatial resolution product. The drawback is that there are extensive data requirements, very extensive, and extensive processing requirements that sometimes require trade-offs to be made in the way that these models are processed. So a little bit about the physical properties that are required to run these models. Most of these models need climate, land cover, topography, and soil property information. And with regards to applying these models across the continental US, most of the necessary information is there. But if you want to apply these models at a high resolution, note that these data sets are relatively coarse in scale. So for fine scale application, you typically require on-site data collection. A little bit on the soil properties that are required to run these models. Soil property information is very important for these process-based models. Primarily, one of the most important soil properties is your textural classifications. And from there, a lot of other properties can be assumed, but it's very helpful to also have your hydraulic conductivity information about soil depth and rock fragment percentages. And you can imagine how these 4 factors work together to give us a better idea of how much water these soils can actually hold and how water moves through these soils. And where is this information acquired from? It's typically acquired from localized soil maps in the landscapes that I'm looking at. You can get some of this information from federal transfer functions. A lot of people, I repeat, a lot of people rely on NRCS data sources for their soil information. The one I'm interested in most is the Surgo data product, but there are other products from them. There's also Polaris remapping of Surgo that's very useful for people. And there are disaggregation schemes that people use to try to get at these data sets. This slide's a little controversial. I don't want to get the terminology wrong, but soil mapping has its roots in land valuation for the purposes of taxation and agronomic planning. And basically the idea I'm trying to get across here is that the eye has primarily been on landscapes that are accessible, agricultural landscapes and landscapes that we can get to. And because of this, forest landscapes tend to have the least amount of soils information, relatively speaking. There is a rich body of forest soils literature. I don't want to imply that there isn't. Dense vegetation also makes these landscapes amongst the most difficult to traverse and measure, which is one of the reasons we don't have that much information. And as I mentioned previously, satellites tend to have difficulty in dense vegetation, high relief. So these remote landscapes that we can't get to, we can't necessarily rely on the remote sensing too much. And then just to reiterate, densely vegetated high relief landscapes are mountain forests, which is what we're interested in. So a little bit about the project objective, what I work on. I've reworded the objective just to make it more digestible. But my main objective is to accurately predict soil moisture at the watershed scale across landscapes using widely available data sets, NRCS soil survey products, and a transferable methodology suited for forested landscapes. Phrased as a research question, it's will the incorporation of newly developed digital soil map products improve the performance of a calibrated hydrologic model with regards to soil moisture prediction in forested landscapes? Our research sites are primarily the Hubbard Brook Experimental Forest and the Coweta Hydrologic Laboratory, which were historically LTERs, so there's a wealth of environmental information there. And we also have an additional site which we're trying to expand to, the Fresno Experimental Forest. The difference between the green and red dots are just that the Coweta and Hubbard Brook Experimental Forests have these new digital soil map products which we can test out, whereas for the Fresno, they're still to be developed. A little bit about background of Coweta Hydrologic Laboratory, why it's so valuable for this type of work. It's primarily its weirs. We have control watersheds, treatment watersheds, 32 weirs on that landscape, 16 of which are still operational. So we have long stream flow data sets for these process-based models to validate and calibrate them. In addition to stream flow, there's stream chemistry data sets that are also helpful for these models, and an abundance of other ecological data sets that are useful depending on how you wish to calibrate these models. Notably for Coweta, there's soil moisture data set that's historically available. I know you've heard about some data sets that I've provided. It's actually just the data that's been cataloged for that landscape. The PI for that landscape that I've been using the data from is, sorry, I don't want to get his name wrong. It's Caldwell. But I've been using data from previous researchers, and that's what allows us to apply these models within these landscapes without having our validation data available. And the story is very similar for the Hubbard Brook landscape. It is currently an LTER, so there's a wealth of other ecological information being collected on that landscape. And we also have those very long stream flow data sets available that are very important for these process-based models. There are also some soil moisture data sets available on that landscape, and that also helps us with the application and calibration of our models. So when I came into this project, I was giving a handful of models for consideration. I'll just talk a little bit about their differences and not go too much into them. Essentially, what these models have in common is that they're watershed scale models, or they can be applied at the watershed scale. So thinking about models that can be applied at 30 meters, as opposed to models that you apply at kilometer scales. One of the models that I had to look at was SWOT. One of the reasons it's not necessarily suitable for the landscapes of interest is because it's not known to be very accurate at that patch scale, and water isn't redistributed via the SWOT framework in a way that's useful for these high relief systems. There's the Newhall model, which you saw a presentation on earlier. You saw a presentation on the R Newhall and their expansion of it. But primarily this model is thought of a point scale model. And while development has been made to expand it to give you spatial soil moisture estimates, it still does not redistribute water in the way that's useful for these mountainous landscapes. And then there's the two models on the bottom, the DHSVM and RESIS. DHSVM, the distributed hydrology soil vegetation model, is super, it was created for these landscapes. So it's well suited for these landscapes, but it's very data hungry and a little difficult to apply. And there's the RESIS model, which was also created for these densely vegetated high relief landscapes. Also a little difficult to apply, but it's super useful. And of these four, the two that we decided to focus on were the RESIS and DHSVM. And ultimately just went with RESIS because it has aspects of DHSVM folded into the way it functions. And it has been applied to the Coweta landscape. And in the publications from the Coweta landscape, it was found to predict soil moisture well at the 3 locations in which they measured. The caveat being that they calibrated that model using their local soil information, which isn't necessarily what's available for other landscapes. So I'm going to skip that. Just to key in on the soil textural map inputs, this is the main thing that's changing amongst our model runs. Soil moisture prediction is heavily dependent on the physical properties that are used as inputs into the model. And new raster soil survey products provide us new soils interpretations of the landscape. So I just wanted to highlight the NRCS digital soil map products. You've heard about their DSS initiative. This can also be referred to as their raster soil survey. I'm sorry, I don't want to get the terms wrong. I'll just call them digital soil map products. And they utilize new observations and new pedologic modeling techniques to create spatial representations of soils on the landscapes of interest. Essentially, what these are returning is just new soils maps that, in my opinion, comport more closely with our understanding of soils on these smaller spatial scales. And what you can see in the figures that are highlighted to the right are just what the RESIS inputs look like depending on what our soils and map is. Unfortunately, these have been simplified into our textural classes. That's just a consequence of how it has to be input into the RESIS model. And for future iterations, we're just going to go ahead and try to incorporate all of the information that's available via the Sergo or DSM databases. And yeah, I'll just skip past this for now. And then slide on the stream flow and soil moisture outputs, preliminary outputs that we're getting from this. I didn't want to not show any data, but the data we're getting isn't very great at the moment. Our fits to stream flow are satisfactory, and they're constantly improving with the modifications we make to the way that we interpret the soils information that we're getting. But I would say that the predicted basin scale soil moisture is still not satisfactory. And this is obvious. High resolution soil moisture prediction is very difficult with coarse scale input variables. But as mentioned, the varying soil map interpretations have helped, and it's a continuing process how best to interpret this soils information to convert it to something that's useful for the model, and then just to get the appropriate output. Yeah, resulting spatial soil moisture prediction is highly dependent on the input soil maps and your model calibration, of course. Skip past that. Apologize. One of the nicer things that's coming out of this study, or more interesting things that's coming out of this work, is the supplementary validation data sets that are being deployed in these landscapes of interest. Soil moisture data sets can be elusive, even in these highly researched forests. We have these super long stream flow data sets, but there's not very long soil moisture data sets for these landscapes. And while there are soil moisture data sets available, additional soil moisture data is necessary for model validation. And just going into how these additional data sets differ from what's already available on the landscape. So like, why don't we just use what's already there? The spatial distribution. These additional data sets are more densely distributed within our watersheds of interest. So we're able to key in on those different soil map units and see how they vary with regard to their response to things like precipitation. We're getting these measurements at the time intervals that we want and we require. We're getting them at the depths that we require. For example, the historic measurements on the Hubbard Brook landscape are only going down to 20 centimeters max. So we're able to get down to 80 centimeters down to bedrock, which is necessary. And importantly, these validation data sets are under the canopy. It's been noted that a lot of the data sets that are collected by other networks are not under canopy. And it can be argued as to how important this is, but it is a notable difference. A lot of words here, so I'll just key in on the titles. One of the biggest challenges of utilizing these process-based models at this high resolution is just the aspect of transferability, making decisions that allow you to transfer to use this model in these different landscapes. Just affects model performance greatly. It's a lot more helpful when you can finely tune your model to the specific forest that you're looking at. CONUS scales data sets aren't often fine-tuned to the needs of specific areas. You can imagine that your DayMet doesn't necessarily capture your local rain that well. Required and available data is not always a one-to-one match. The Sergo map unit data is very valuable, very useful, but it's not a soil hydraulic property map. You have to make a lot of decisions to convert it to that, and those decisions have consequences. And there are efforts being made to provide clearer interpretations. I just wanted to highlight some of the work by Dylan Beaudet and John Maynard. Fortunately, I can't talk too much about it because I don't have time. And another notable thing is just that when switching between models, the outputs aren't necessarily a one-on-one match. So it's a little difficult to actually validate them. So it's just great to have additional data. So I'm going over my time. I'm sorry. I'll just go over the takeaways really quickly. Process-based modeling is not the only solution. There are other modeling approaches that can be taken, but what we need is more data to apply them. Process-based models require a significant amount of input data, difficult to acquire over the continental US, although efforts are being made to acquire these 30-meter data sets that will allow us to predict soil moisture at finer scales. It's very important to define scale when doing this research. These models function at different scales, and you can imagine that different processes are important when thinking about different scales. Preliminary data is showing that the updated soil maps do improve our spatial soil moisture prediction. I have to do more robust analyses of that data, of course, but I do believe that these new digital soil maps provide great potential for soil moisture prediction. I think data assimilation approaches are very notable and useful. That three-legged stool, we shouldn't only be focusing on one leg, not only focus on models, focus on approaches that assimilate the satellite measurements and the modeling approaches just to correct. And then we need more soil moisture data. Even in the landscapes that I studied, there's not that much soil moisture information. So we just need more of these networks across the US. And that's it for my presentation. Are there any questions?
Thank you. So the U.S. Global Change Research Program's Integrated Water Cycle Group is working on an integrated hydroterrestrial modeling workshop. And the goal is for us to connect models that explore different parts of the water cycle so that, as you said, if you need a lot of input data, you can just hook up the outputs from a different set of data sets, forcing, for example, and then your responses can go into more downstream users, such as flood resilience. So where do you see as the opportunities or gaps of opportunities for these interoperable data systems to happen?
Well, I guess the first gap is just communicating with people. One of the things that was talked about is terminology, making sure people are using the same terminology, just to make sure that when this information is being stored, it actually means what people think it means, and that will just enable people to communicate and share their data more freely. Kind of answers your question, kind of doesn't. Sorry about that.
We can chat afterwards.
Yeah.
Hi. Go ahead.
Another question.
Yeah, another question. And then this might be a little bit more technical, and so maybe I can check later too. But we know that most of the hydrological model or the research that you're using is not necessarily designed to model soil moisture. So so I want to hear from you in terms of when you try to calibrate. I know the result was not that great, but then what's your strategy of trying to calibrate it? Is it actually any parameter was able to address the changing soil moisture in your cases?
Model sensitivity tends to vary based on the models we're looking at. For the RESIS model, the calibration is primarily based on that stream flow data set that we're getting. We're also looking at the soil moisture for calibration, and of course, their vegetation dynamics modify the way that water flows in that model. So that's very significant. I've been wrestling a lot with the vegetation and possibly incorporating FIA data as opposed to the national land cover data, just to get a better idea of how that functions. But the validation is primarily based on stream flow, and that's why those sites are so valuable. We have those stream flow data sets.